Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll continue Chapter 7 on categorical data analysis, inference, and hypothesis tests for single proportion problems. So let's assume that you're interested in estimating the proportion of individuals in a population with a certain characteristic or attribute based on a random sample of size n from that population. So P is the true proportion of interest in the population, and we're going to estimate that with a sample proportion called P hat. The hat over P indicates that this is an estimate of the true population proportion. And it's easy to calculate. You simply take the number of observations that have the particular attribute of interest and divide by the total sample size. So in the Titanic example on the previous page, at the end of the previous video, we were looking at the probability of, or the number of successes, or what is success here is survival, the number of people who survived the sinking of the Titanic. We can call that a success, and the people who did not survive, we'll call that a failure. And if we're interested in estimating the probability or proportion of people who would survive such a sinkage, then we can count up how many people actually survived, okay, and then divide by the total number of people on the ship. And that is our estimate for survival. So this is the simplest such categorical data problem, where we've got two categories that we call success and failure. Okay? And the words successes and failure are don't necessarily mean good and bad. For example, if you're interested to know how many insects, die after 1 hour after you apply a certain poison, you could consider a success that the insects died and a failure that they continued to survive. Or you could relabel it. So a success might be in favor of the insects, that they survived, and a failure that they died. It depends on the point of view. And typically we are modeling the probability of success, so we want to label the outcome to be success for the thing that we're interested in, and failure is everything else. And it doesn't even, you can take something with many categories and still make it binary. For example, there may be lots of hair colors, for example, and perhaps a success is choosing someone at random who has black hair, and a failure being choosing someone with everything else, blonde, brown, etc. And so success and failure obviously there don't indicate characteristics of the people you chose, but we're interested in estimating the proportion of people with black hair. And so seeing an observation with black hair is a success. All right, that is plenty on that. So we're going to model the probability of success with P. Okay, so that's the population proportion P. And then therefore the complement of that, the probability of failure, is going to be 1 minus P, because probabilities must add up to 1, or 100%. Right. So let's start with calculating a confidence interval for the true population proportion P. So if we're interested in estimating what the population proportion P is, we would draw a random sample, calculate a confidence interval, and then interpret that confidence interval that is sort of the likely range for where the true population parameter is. So we have the standard set of steps for a confidence interval. We want to specify the confidence level. So alpha we might specify as, say, 0.05, and if we subtract that from 1, we get 0.95, multiply that by 100, this is a 95% confidence interval. We can compute a critical value, which is used for the equation. R is just going to sort of give this to us. In proportion tests, we don't use the t-test or the t-distribution anymore. Instead, we use the normal distribution. So one way of calculating those quantiles is with Q-norm. That's for the quantile from the normal distribution, and 1.96 is the number for a 95% interval. Then we're going to calculate the standard error, and from there we'll calculate the lower and upper bounds. So basically p hat, our estimate, plus or minus as the z critical value. That's telling us that we're going to go out almost 2 standard deviations. And then the standard error of our estimate. And our standard error, in proportion problems, it's interesting, we don't have separate numbers for both the mean and the variance. Instead, we only have the number of successes divided by the total sample size. So the mean and the variance are related to each other. So we have p hat, which is the estimate of the mean, and then we have a function of p hat, which is the estimate of the variance. So p times 1 minus p is the variance. When we divide that, I guess there's some details here I'm going to skip over, but so so the standard error of our estimate is p times 1 minus p divided by n, take the square root. And so that's basically an estimate of the standard deviation of our estimate p hat. And so finally we can calculate our confidence interval. R is going to give all this to us. So let's have a quick reminder as to the interpretation of confidence intervals. So the confidence interval is determined once the confidence level is specified and the data are collected. Keep in mind here the randomness is actually the data collection process. Everything else is fixed. So prior to collecting the data, the confidence interval is unknown and can be viewed as random. So it's the interval that's random. Maybe just as a quick point here, the population proportion p, how about here, in the statistics that we're learning, p is a fixed number. That's a true number in nature, but it's unknown. So fixed meaning it's not random, but we don't know what it is. So we draw a sample, we calculate an estimate, and then I'm paging down now, for inference we calculate a confidence interval. And it's in this confidence interval, the confidence interval is random because it's based on the random sample, and that sampling procedure is random. Okay? So different samples will give different confidence intervals, and the confidence, the word confidence means that what proportion of the confidence intervals would actually contain the true value. And so in 95%, a 95% confidence interval will have a 5% error rate, which means that if you repeatedly sample the population and construct 95% confidence intervals, one after the other, then 95% of those intervals will contain the true population parameter, and 5% will not contain it. And so you're either right, if you got lucky, or you're not. And unfortunately, you never get to know the answer. So you're either right or wrong. All right. Very good. All right. A couple short points here. The standard error is actually largest when p is close to 0.5. And so if p is a half, this is going to be p. This is going to be a half times 1 minus a half, which is also a half. So the numerator is 1/4 divided by n. When you have numbers that are smaller than or bigger than a half, say 0.1, this would be 0.1 times 0.9, which is 0.09. Great, I still got it. And 0.09 is quite a bit smaller than a quarter. So this actually has like an upside down U-shaped curve if you calculate the standard error as a function of the population estimated proportion p. And that sort of makes sense because if you get 1/2 for p, you're close to the center of the range from 0 to 1. And so you have the most wiggle room around you at a half. If you've got a proportion that's close to 0, say like 0.1 or 0.01, you can't wiggle that much because you start to hit the boundary at 0. and so the variance has to be small. Otherwise, you'd run into 0, or it would be impossible to go over. So you end up with this constraint at the boundaries. All right, so let's look at an example. And I'm going to page down for a second. We're going to do this by hand. We're going to do the confidence interval. We're going to do a hypothesis test, and then we're going to come back, I believe, and implement this in R at the end. All right. So that's where we're going. Here we are. All right. Tamper-resistant packaging. So in 1983, I actually sort of remember this as a child. Tylenol. There was a Tylenol poisoning episode, and it became a big deal. It was highlighted in the media, and there became this desirability to use tamper-resistant packaging. So before then, there wasn't all the foil on medicines and things like that. You just open it, and the pills would fall out. You wouldn't have this additional blister seal packaging. And so there was an article about tamper-resistant packaging. Is it really tamper-resistant? So we want to know whether you could, tamper with that special type of packaging, and whether people cared. Okay, so we surveyed consumer attitudes toward the packaging. So we got a sample of 270 consumers, and whom were asked the question, would you be willing to pay extra for tamper-resistant packaging? Now keep in mind this is after a poisoning episode, and so people over-respond, and so this is what the result is. The number of yes respondents was 189. So if we call success that they say yes, that they would be willing to pay extra, then the number of successes are 189 out of 127. So let's calculate what a 95% confidence interval is for the true population of proportion of all consumers willing to pay extra, at least back in 1983. So we've got a sample size of 270. We had number of successes as 189. You calculate that ratio. 70% of people are willing to pay extra. This is great news for manufacturers because it doesn't cost that much to make tamper-resistant packaging, but you can charge quite a bit more for that. Good news. All right. Going through a 95% confidence interval, we calculate a z-statistic of 1.96. That's going to come up over and over again throughout this. And the standard error is, if we page up for a second and look at the formula, we've got the estimated proportion of success times the estimated proportion of failure, which is 1 minus success, divided by n and the square root. So we're going to plug in our p hats in this formula, paging back down. So our estimate of success was 70%. So here's 0.7 times 1 minus 0.7, which is 0.3, and so on. And we get these standard errors. They'll tend to be small because we're constrained for proportions to be between 0 and 1. So 0.028. And so if you look at the entire margin of error, this product, it's about 0.055. So our confidence interval for the population proportion is 0.7 plus or minus 0.055. And so we're 95% confidence that the proportion of people willing to pay extra is somewhere between about 65% and 76%. Now, we don't know how much they're willing to pay more, but we know that there's some desire for this added level of protection. So not bad. We drew a sample of 270 people. Possibly takes an afternoon to sample that many people. And we have, within 10 percentage points, 11 percentage points, an estimate of the population parameter. Pretty good. So, model assumptions. How do we know that this procedure was appropriate? So, we are going to see a few different versions of proportion confidence intervals and tests. And when you have large sample sizes, and proportions that are close to a half, we can use a normal approximation to an exact interval or exact test using the binomial distribution. So these proportion problems follow the binomial distribution, but the normal distribution, which we know and love as the bell curve, estimates the binomial quite well. So how do we know we can use this sort of equation? Note if you solve this equation for p hat, you basically get like a confidence interval. So the rule of thumb here is that if you have n times p hat that's greater than 0.5 and n minus 1 minus p hat, that's the probability of failure, that's greater than 5, then the normal approximation should not have very much error relative to the exact distribution. So this is actually pretty easy to get. If p hat was a half, okay, you would need 10 people to a sample size of 10. If p was a quarter, you need a sample size of about 20, and so on. Right? So if we check our own numbers or NP hats of successes and failures, we get 189 and 81. Both of those are greater than 5, so we're doing good to use the normal approximation here. And the normal approximation, where did we use that? We used that when we calculated this bound 1.96 for the form of the confidence interval, where the estimate p hat plus or minus z times the standard error, this 1.96 is coming from the normal distribution. All right. So that's a confidence interval. Let's look at a hypothesis test, or an hypothesis test, as you might say in England. So let's look at a question. Environmental problems associated with leaded gasolines. So this was back in the 60s, 70s, 80s, until leaded gasolines were phased out. And there were many well-known problems with leaded gasolines. Many motorists were tampering with their emission control devices on their cars to save money by purchasing leaded gasoline, because leaded was less expensive than unleaded gasoline. And back in those times, the handle that you would put, nozzle that you would put into your car, they were different sizes. So I think the leaded gasoline had a large nozzle, and unleaded had a narrower nozzle. So you couldn't get the leaded nozzle into the unleaded gasoline receptacle on your car. And so people would swap those out illegally. So in LA, in the middle of the 80s, there was a report that said that 15% of all California motorists had engaged in emissions tampering. Okay, so that we're setting up the hypothesis right here in this report. So we want to know, is 15, an accurate estimate? So we're going to conduct our own random sample of 200 cars from LA and check the emissions devices on them and see whether they were tampered with or not. And of those 200, we found that 21 were tampered with. All right, so far we're looking at something that's about 10%. And so is that enough evidence to say that the LA Times estimate of 15% is incorrect or not? All right, so that's the, or at least this 15%, I should read my own notes here. This 15% is for all California motorists. Okay, and we took a random sample of folks from LA County, and so the question here is the proportion in LA different from the statewide average, or proportion? By the way, a proportion is is the mean of zeros and ones, where successes are coded as ones and failures are coded as zeros. So the proportion of ones is the same as the mean of those zeros and ones. All right, so let's perform a hypothesis test. Same as a t-test from back in chapters 2 and 3. So let's say we're interested in whether the population proportion P is equal to a pre-specified hypothesized value P naught. And so we can specify the hypothesis, H naught is P equals P naught versus the alternative of not equal. You can also do one-sided hypothesis tests here. Choose the size or significance level of the test. So, for example, alpha equals 0.05. We can calculate a critical value for this, and finally a test statistic, which is our estimate minus our hypothesized value divided by the standard error. This is our Z statistic. I've got a subscript S here for for statistic. Sometimes it's also Z observed. It's the observed statistic. Finally, the standard error is this, and it looks the same as before, except for the standard error here. Keep in mind that when you do a hypothesis test, we assume that the null hypothesis is correct. Oops, excuse me, I hit the wrong key. And so under the null hypothesis, the true population proportion P equals P naught. Therefore, the calculation of the standard error is based on P naught. That's under the assumption that the null hypothesis is true. So that is a difference between testing and inference. If I page up for a moment, when we calculated our confidence interval, we used our estimate with a confidence interval because we didn't have a hypothesis. So that was our best guess for the proportion. But now if I page back down, we have a hypothesis and we're assuming it's true, so we're using that value for our standard error. Finally, we reject based on standard rules. If your observed value of our statistic is more extreme than our critical value, then we reject. Alternatively, if your p-value is less than 0.05, your alpha value, then we will reject. And this comment here is about the difference between p naught and p hat in the standard error, which I just emphasized. All right. So here's a normal distribution, also known as a Z distribution. And you can use this critical value, which is often, say, 1.96, almost 2 units away, with tail probabilities equal to 0.05 over 2, as the rejection region. So if you fall outside that rejection region, then you reject the null. Alternatively, you can do things based on the p-values. So wherever your Z statistic was, then you calculate the area more extreme than the absolute value of the Z statistic and add those two areas together to get your p-value and compare your p-value against alpha. All right, so that's pretty much what this small section says. So if we return to our missions data example, we've got our car data, we've got our null hypothesis that the true population proportion is 0.15, and the alternative is that somehow LA proportion is different from the entire California proportion. We're going to set our alpha level to 0.05, which gives us a critical value of 1.96. We observed 200 cars, and 21 of them were tampered with, giving an estimated proportion of 10.5%. If you calculate our Z statistic, we have our observed proportion of 10.5 minus our hypothesized proportion, 0.15, divided by a standard error that we calculated. I didn't show you that calculation, but there it is. Our Z statistics, negative 1.78. So without comparing it to what's extreme, we tend to think of about 2 units as being extreme and less than 2 units as being not very extreme. In this case, 2 units is actually the value is actually 1.96. And so it's not as extreme as 1.96, so we don't have enough evidence that it's different from the null hypothesis here. Oh, there's our calculation of the standard error. And given that either the observed statistic was less than our cutoff, or that our p-value of 0.075 is too big, bigger than 0.05, then both of those reinforce the decision of failing to reject the null. Okay, so we have insufficient evidence to reject the null at 0.05. So here's our interpretation of the test. We need to give the evidence for our decision. So given that the z-statistic is not very extreme, this is going to be the more common way to say, so start the sentence instead with the p-value was 0.075, which is greater than 0.05. Therefore, we have insufficient evidence to reject the null at 0.05 level. So that's the evidence in the decision. The second statement is always in the context of the problem. So that is, we have insufficient evidence to conclude that the proportion of cars in LA differs from the statewide proportion. So, yeah, so basically it seems that the LA county is representative of the entire state. Here's what the p-value looks like. For this data, we observed a statistic of negative 1.78, and then we calculated the tail probability, what's more extreme than 1.78 in the negative direction and in the positive direction. We add up those two tail probabilities, and it adds up to 0.075. Because that's bigger than 0.05, it's consistent with the null. Basically, it's not different enough from 0 to say it's to reject the null. All right. Just as a quick remark, because the standard error used in the hypothesis test and the confidence interval are different, right? The difference between using p-hat for the confidence interval and p-naught in the hypothesis test when we calculate the standard error, it's possible for borderline cases where you've got p-values that are close to 0.05, for example, that the decision between your hypothesis test and whether or not the hypothesized value falls in the confidence interval can actually contradict. Recall that back in Chapter 2, when we did one sample t-tests, that if the confidence interval contained the hypothesized value, then that suggests that the hypothesized value is consistent with the data, or that the data is consistent with the hypothesis. Okay, if the hypothesized value is inside the interval. If the hypothesized value is outside the interval, then it suggests that the data is inconsistent with the null hypothesis. But it's possible in this case, because we've got different values going into the calculation of standard error, that you get differences. That rarely happens, but don't be surprised. That means that you need to be clear about whether you are conducting a hypothesis test or a confidence interval. So what your goal is determines how you answer that question. Am I making inference with a confidence interval, or am I testing something? All right. Finally, the appropriateness of the hypothesis test is the same as for the confidence interval, except instead of p-hat, we're going to use p-naught. So if your sample size times your hypothesized proportion is greater than 5, and for success and for failure, if they're both greater than 5, then you can use a normal approximation. If not, there's also functions in R to do an exact test. All right, so let's see this in R, and believe it or not, that's the whole thing. So it's so simple. So there's prop test, so that's the proportion test, and the prop test function gives us an approximation, a normal approximation for the proportion test. And the arguments here are the number of successes, 21, out of 200, that's the total sample size, P equals is the hypothesized value, and whether correct equals true or false, right? So this is one of those issues where if we say false, then we can use the standard normal hypothesis approximation that you would have learned in Stat 145. And then lots of people have worked to slightly improve that test. And so there's a Yates continuity correction, which I'm not going to explain, that if you put true in here, you get slightly different values. In practice, it's rarely going to matter very much. Okay? So the output from this one line of code is everything we need. So we've got it reports to us that we're doing a one sample proportion test without continuity correction. Our data is 21 successes out of 200 observations. The null probability is 0.15, comes from this, p equals 1.15. And then some statistics. So there's a chi-square test statistic that's being used here. By the way, if you take the square root of this, you get the z statistic, at least the absolute value of the z statistic. It's a 1 degree of freedom test. Here's our p-value of 0.074. That was the 0.05 that we saw earlier. The alternative hypothesis is not equal. That's the default here. You could also specify another argument of alternative is greater or less than. We've got a 95% confidence interval right here, so 0.07 roughly to 0.155. And of course our sample estimate, which is just 21 divided by 200, is here at the bottom. So we've got all the information here to either make a decision about a hypothesis test or to make inference using a confidence interval. All right. The last section I believe here is that you can specify one-sided tests and one-sided confidence bounds. So if you're interested in that, I'll recommend that you go ahead and read through this. Okay, a one-sided p-value or one-sided confidence interval will be just a single tail, so that you won't include the other side. And the way to specify that is with the alternative equals either greater or less as an argument there. All right. When you have small samples, then our rule of thumb won't be met. Do I have that rule of thumb identified here? No. So remember, the rule of thumb is that we need at least, sorry, I'm jumping up and down here, at least the sample size times the proportion for success and for failure both greater than or equal to 5. So if that wasn't met, if it was less than 5, then we wouldn't be able to use the normal approximation. Okay? And you'd have to do something different. So I'm going to page down. All right. And we'll talk about small sample procedures. So something that's not really used anymore, this was back in the day when we didn't have very powerful computers and people were doing these calculations on hand calculators at best, was when you didn't have your assumptions met, you would simply add 2 to both the successes and failures. And this is a strategy suggested by Alan Agrisi, he's a statistician. But we don't really use this anymore. So that's just sort of a historical note. Instead, I'm going to show you what the exact test looks like through this swimming segregation example. And so this is a true data example based on a case heard from the U.S. Supreme Court about racial segregation in a swimming club, so high stakes, and about the probability of being admitted to the swimming club based on what your race was. Right? So we want to know whether a racially segregated swimming club that was ordered to admit minority members has held up its side of that decision. All right. So historically, 85% of white applicants were approved. Okay, and since the mandate, only 1 out of 6 minority applicants were approved. And so if, in fact, the probability of being admitted didn't depend on race, then we would expect not just white applicants to have an 85% approval rate, but also everyone else. And 1 out of 6, to my mind, is far away from 85%, almost the inverse of that. So, is there evidence of continued discrimination? So we can perform either a confidence interval or a hypothesis test to answer this. So let's, I'm going to scroll down. You can read through this here, but I'm going to show you how to do this in R. All right. So here is the proportion test, and we're going to run it with 1 success and 6 trials. Here's the hypothesized proportion of 0.85 that we're comparing our minority applicants to, and we're going to output the confidence interval from this proportion test. And notice pink, warning in prop test. The chi-square approximation may be incorrect. And why is this? Well, we don't have, so we've got a p-naught of 0.85. If we multiply that by the number of successes, 1, and the number of failures, which is 6 minus 1 equals 5, we don't get at least 5 for each of those. In particular, for numbers of successes, 1 times 0.85 is 0.85. So it's too small. So we get a warning that says this confidence interval may not be appropriate, and I would not use it. In fact, even the Agrese's method's not going to get us big enough if we add 2 to the successes and failures each. So the way to solve this problem is with the binomial exact test. And in fact, this is always preferred over the normal approximation, though once you get fairly large sample sizes, the difference between the exact test and the normal approximation tends not to be very important. But this historically has been very prohibitive because it was hard to calculate, but computers today are fast and powerful. So here is our confidence interval for our exact test. Yeah, I've chosen to output the confidence interval. Anyway, so here we've got a confidence interval for our minorities for the true proportion of being admitted. It goes from 0.004, which is basically 0, up to 64%. Okay? We can also look at the hypothesis test. So notice that it doesn't include 0.85, right? But one comment I made earlier is that hypothesis test and confidence intervals are not equivalent for making a hypothesis test decision. So, but anyway, so there's a confidence interval. Here is finally the hypothesis that we want to test. Let's test it for discrimination. So the null hypothesis would be that for minorities, the acceptance rate of 0.85 is the same as for whites. And the alternative is that there's discrimination, which indicates that minorities are being accepted with lower rates than their white counterparts. And we'll use an exact test. So here it's the same binomial test, but we're specifying an alternative of less than. And our hypothesized value is 0.85, and here's the output. So we've got 1 and 6 as the successes and total numbers, and it verifies that for us right here. Number of successes equals 1, number of trials equals 6. Here's our p-value, 0.0004. Quite a bit smaller than 0.05. We're going to reject our null hypothesis in favor of alternative, and that's bad news. The alternative is that there's discrimination still happening. So that's everything you could want to know about one sample tests. The next video will be, you know what, this is such a short section. Let me just tack it on right here. So analyzing raw data. Sometimes data is stored in a spreadsheet with one observation per individual. Notice that all the previous examples, I had summarized data already, the number of successes and the total number. So instead, so here we've already counted up and summarized our successes and failures. When you've got raw data, so here's a swimming example, then you've got a then you can you need to do a step, an extra step for the counting. All right. So let's create this data set. It's just a list of text. There's not approved and approved. And one danger here is that you've got spaces, and we want to make sure that the delimiter for each row is not a space. The default delimiter in read table is a space. So if you try to read this with just read table, you would get 2 columns here for the not approved, and you'd get just a single column for approved, and then possibly an error that not every row had the same number of columns. And so what I've added here is a separator argument to say that separators are commas. Basically all I'm saying is that it's not a space. And so it treats this entire text string, including the space, as one chunk. There's no header to this data. I'm going to add a column name to the swim data called application. So you put in the application, it was either approved or not approved. And the structure of this data set is text. So there's one column called application, and it is a character string, and these are the values: not approved, not approved, not approved, approved, and so on. And when you display the data frame, it looks just like the original data above. Finally, you can use the table function to count the frequencies of each category. So we've got number approved is 1, the number not approved is 5, and in order to use, say, the binomial or the proportion test, you can put in a single object, which is a table. And so this table, we already saw above, creates these two numbers, a 1 and a 5. And if those two numbers are a single object with two numbers, you put that in as a single argument, and you'll get the same test as if you had counted up the number of successes, 1, and the total number, 6, and added that as 2 separate arguments. All right. So if you compare all these numbers here, they are the same as what we saw earlier. In particular, there's the p-value of 0.0004. All right. There is a possibility that the order alphabetically is wrong. For example, we might have accidentally estimated the probability of failure instead of the probability of success. So you have to be concerned about the order here. The first category, approved, is success, and the second category is failure. And you might try to be clever here to alphabetize them so that success has is earlier in the alphabet than the failures. All right, that is everything I wanted to tell you. If you know something about the binomial distribution, perhaps because you've taken Stat 345 in probability, you'll see that for the cumulative probability distribution, that is the area to the left of a certain number under the binomial distribution. So we had 1 out of 6, and this number right here is, times 10 to the negative 4th, it is 0.0004. It's the same number we had as the p-value right here. So that's just describing where the p-values come from for the exact test. All right, you hung in there to the very end. I'm proud of you. We'll come back in the next video and talk about goodness of fit tests, which is when you've got multiple categories and you want to know if the proportions across all those categories fit some particular distribution.